In this lesson, we'll discuss the methods used to implement the response rate estimating worksheet. We'll use the experience in running the worksheet and the theoretical terms we defined in the earlier lecture to discuss how the valuation worksheet is implemented and how the planning worksheet is implemented. The reason to know this is to be aware of the limitations in the method. First, we'll work on the evaluation worksheet. In the valuation worksheet, the user enters the complete outcomes of two actual campaigns. That is, the number of actions sent to each campaign, the number of successes in each campaign, and the valuation of success in each campaign. The worksheet shows the actual posterior distribution of the unknown true values of the campaign populations, assuming a Bayesian Jeffreys prior. It also shows the probability of the first campaign being the larger and the probability of each campaign exceeding a user-supplied optimistic target. The priors are one of the Achilles heels of Bayesian methods. Bayesian reasoning itself is rock solid, but it requires a correct prior from the user. If the prior is sufficiently wrong, the rest of the reasoning is also wrong. One of the triumphs of the more common frequentist statistical methods is they are correct without the need of a user-supplied prior. However, I like Bayesian methods, and I'm going to say don't worry about the priors. The Bernstein-von Mises theorem states under fairly mild conditions, the data eventually swamps the prior. That means the outcome is usually not that sensitive to your choice of priors. By a theory called conjugate distributions, we know a Bayesian update on a beta priored measurement with count data gives us a beta posterior. Combine that with the Bernstein-von Mises theorem, we know that any distribution that obeys some mild conditions must be approaching a beta posterior under this update regime. Therefore, beta is a very appropriate distribution. The prior we used was the Jeffreys prior. It is one of the so-called non-informative priors. It has some good properties. We apply the same prior to all campaigns, and the Jeffreys prior is easily overwhelmed by data. It has some bad properties also. This prior doesn't incorporate actual expert knowledge. Statements like, I have never seen a campaign of this type have a response rate over 3%. So inference using this prior may not be as statistically efficient as a method that allows this extra information in. Also, if you have a campaign with n actions and 0 successes, the Jeffreys prior thinks it has a success rate of 1 over 2n. So until you have n large enough, you don't care. You see a bit of an upward bias in all the estimates. The quick way of saying everything above is the system is a Bayesian analysis where we use the actual campaign outcomes to get the exact posterior distributions of the unknown campaign success rates, assuming an uninformative Jeffreys prior. The math of the planning worksheet is actually easier. The user supplies campaign sizes, assumed campaign values per success, and the actual values of the unknown rates. Given so much, it's just a simple matter of forward simulation or using the binomial distribution to get every possible outcome and their probabilities. That is, for every possible count of successes, how likely is that count? We don't actually expect the user to know these unknown rates. We're being a bit of a bully asking them for them. What the user can do is type in rates from previous campaigns or commission a pilot campaign to get estimates of these rates. Our main tactic here is the principle of revenue indifference. The example is, if you've been selling an item for $1 historically, then you know the response rate for that item. So if you want to compare a $1 campaign to a $2 campaign, you enter the known value for the $1 campaign, because you've previously done it, and you just assume that the $2 campaign converts at half the rate, because this is the rate that you'd be revenue indifferent. You critically want to know whether the second campaign converts at more than half the rate of the first campaign, because it's exactly where it becomes more profitable. The role of the pilot campaign, or even knowledge from previous campaigns, is to get a lower bound on the response rates you expect. As we've seen in working the worksheet, the lower the response rate, the more data we need to even get a reasonable count. Sometimes you can get starting counts from the literature, though literature counts are usually much higher than anyone actually experiences. For example, this source claims that email targeting campaigns can have a click rate as high as 3%. But even that could turn out to be a very low rate if we assume that 5% of the people that visit your site go on to purchase, because the 3% click-through rate times the 5% action rate becomes a much, much lower 0.15 email to action composite rate. Throughout these lectures, we've been picking sample sizes to hit a target count, be it 5 successes, 10 successes, or 100 successes. The argument is that in any count-based process, be it from a binomial distribution or a Poisson distribution, the variance is going to be about the same as the mean, especially for large counts. Therefore, the standard deviation will be the square root of the mean. So if the mean is 100 successes expected, the standard deviation will be 10. So by our standard rules of thumb of standard deviation, we expect to be within plus or minus 20 of the true value. Very often. This argument can be done in a normal or student T type argument, or even by directly calling R's binomial code to get how much mass is outside of a range in question. However, the reasoning comes from something called the Poisson paradigm. Basically, count-like distributions look like Poisson distributions. The Poisson distribution measures things like the number of ticks detected by a radiation detector. What it abstracts out from the binomial distribution being the true distribution of what's going on, what it abstracts out is the number of actions. It turns out the most important thing in these trials is not how many actions you send out to try to get the successes, but the number of successes. 3 successes is a very small number, and 200 successes is a moderately large number, no matter how many actions you send out. Though obviously the action rates or the success rates themselves depend on both successes and actions, as it's a fraction. Back to the planning worksheet. There are 2 primary planning columns: suggested experiment sizes to hit expected rate counts, and expected experiment sizes to get the largest campaign down to a given relative error. This is similar to how you would set up a power or significance calculation. However, we are not computing p-values or confidence intervals, but something closer to Bayesian credible intervals. We often fall back to the count-based design because the experiment designed to get the low probability of moderate error is often too expensive to achieve. Because there are so many trade-offs, we think you should play with the sheet. Put in different count sizes, put in different criteria to see how the count sizes change, and see what can you live with. The quick statistical way of saying all above is just using the presumed values, i.e. the values we bullied out of the user, of the unknown campaign success rates. We show the typical sizes of the binomial outcomes. And that's about it. You may want to rewatch the sheet operation lesson now that you've seen a few of the terms in context. Obviously, there are a lot of technical details. We have some writings on various pieces of the puzzle, such as a clear picture of power and significance of A/B tests, when to choose among Bayesian and frequentist methods, bandit formulations for campaign testing, and some puzzles that try to make frequentist inference seem as hard as Bayesian inference always seems to appear. What to take away? If you have a worksheet or calculator, then you shouldn't be worried about the technical difficulties of the calculations. So those calculation difficulties should never be a reason to choose between t-tests and Bayesian methods, or vice versa. With some tools and practice, you should be able to calculate quickly and confidently. I'd like to thank you for taking my course. The next lesson is optional. It is only slides, and it's essentially some references into the code, literature, and other places.